What I want to start out with, and many of you guys got, if not done with exercise 3 or working on exercise 3 in lab 6, and we were talking about this thing, a software interrupt. I don't know if you've kind of noticed it, but this function, SWI has been in your starter code since the beginning of the semester, and we really haven't talked about it at all. And I just want to talk you through it and just show you that it's just another place. There's many ways to write code. We've got our while loop where we can put not as important code or code that needs to be interrupted. That's the main one that we've learned so far. And then we can use these software interrupts to also allow for code that can be interrupted and run a little longer is the point. Okay, so what we're going to be when we get done with exercise 3 of lab 6, this is going to be the flow of our code. What are we going to do? So initializations in main, of course, we set up the ADC, we set up the PWM, we set up the SPIB, all that kind of stuff to get ready to talk to things. But the main thing in main is we set up, well, at least in the flow, set up ePWM 4 to trigger ADC C every 1 millisecond. Okay? So we do that, right? And when we enable interrupts, or actually just tell the PWM4 to start counting, you know, if you set its mode to 3, the counter is frozen. When you set that counter mode to 0, it starts counting up. Okay? And once we do that, it's going to, when it counts up to enough ticks that equal 1 millisecond, which we know is 50,000, isn't it? We've been setting that, the period value to 50,000. When it reaches 50,000, it causes the ADC to trigger. Right? We trigger the ADC, say, go sample. And if we remember, we're sampling SOC 0, SOC 1, SOC 2, SOC 3. And those SOCs are configured to sample the 4 channels of the analog gyro, right? Okay, so then our flow. Every 1 millisecond, right? The ADC is triggered, therefore the ADC C ISR is called when ADC conversion complete. All right? So in a sense, in the flow, this is step 1. Okay? And what I want to show you is this all happens within a millisecond. Okay? So even the last step, we will think of it happening every millisecond, because it does. It happens every millisecond. But anyway, so that's the first C code that occurs, right? So the ADC ISR is called, right, because the ADC conversions are complete. Here, read for SOC results, don't we? This is where we read the results. Okay, but then in addition, so we'll call this like what happens inside A, B, start SPI B communication by what? We know by writing 8 values to SPI TX buff, which is the SPI transmit FIFO, isn't it? Okay? Remember what we did there? We sent 3A ORed with the most significant bit high, so we actually set BA first, and then we set BA00. So BA00 was our first thing we sent over, telling, well, what did we do first? We chip selected it, didn't we? we pulled GPIO 66 low. Then we wrote hex BA00 out to the transmit buffer or the transmit FIFO. Then we sent 0. Then we sent 0, right? Remember we did 7 zeros we wrote to the SPI buffer, didn't we? Okay? And what that does is it puts everything into the transmit FIFO that needs to get shifted across to the MPU 9250 such that it sends us back all the information we're interested in. All right? Okay, good. So 8 values. So let's just put one here. TX buff equals OXBA00. TX buff equals 0. And so on, dot, 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 for, this is the first byte, second, third, down to the 8th, not byte, 16-bit word, right? We're sending out 16 bits at a time. Transmit buff equals 0. Okay, so that's all that's inside our ADC ISR. Okay, every millisecond it's called and it starts the SPI communication. All right, now we actually know how many microseconds later, really close to at least, how many microseconds later our SPI-B ISR will be called. Because what did we do? Also in here, we maybe did it first or at the end here, we said SPI, what is it called? The FIFO interrupt level or something to that effect, right? We set that equal to 8. So that means when the SPI has received 8 things, call the SPI, not in C here, we got to go back to 1. Where's my eraser? Okay, so we actually set it to 8. So the second part of our flow is that SPI-B ISR is called. Okay? But as I said, we know about how much approximately later it's called because we're sending over 8 16-bit things, 8 times 16 bits, and we've set up this communication to happen at 1 megahertz. You could actually kind of play with that a little bit. This MPU 9250 doesn't transmit at really fast SPI rates. There's a lot of chips out there that'll transmit at 10 megahertz, 20 megahertz. This chip, they kind of recommend 1 megahertz, but you could probably go a little bit faster if you needed to. But I'm just being conservative here. So every bit, right, is a clock at 1 megahertz. That gives, this is approximately, obviously 1 microsecond for megahertz. So what do we got? 16 times 8, 16 times 4 is 64, right? So 128, is that right? 8 times 16, am I right on that? 32, 32, 32, 32, right. So 128 microseconds later, so 128, approximately, it'd be a little bit longer than that because you got your time till when the interrupt occurs and all that kind of stuff, but approximately 128 microseconds later, that's when this guy happens, right? Because when we send 8 things, we receive 8 things, don't we? Okay, but still, do you see, this all has to happen within a millisecond. That's a tenth of the time, but still, it's only a tenth of the time, right? Okay, good. Then, in the SPI-B ISR, what do we do? Mainly, we read the IMU readings. So read MPU 9250 data off of the receive, so SPI RX buff, which is the receive FIFO, isn't it? Okay, so we read all that, we convert it to G's, we can convert it to degrees per second. Okay, and then what we're going to do is, once we've got all this data, we're going to call a software interrupt that is going to do all the data crunching for us, decide what our PI control law what our vref and turn are, what our motor torques are to get our robot to go at the speed we want it to, and all that kind of stuff. So again, we're not going to do a huge amount inside SPI BISR. We'll read it, and then B, post SWI1, or whatever we call that function that you're going to do in exercise 3 of lab 6. Okay? So then now the final step in our flow is then this SWI1 highest priority, I called it, or something to that effect. Okay. Now, inside this function, this is where all your algorithms are going to be run. Okay? You're going to do wall following in exercise 5, I think it is, or whatever. You're going to, in lab 8, we're going to tell the robot to go to an XY position, and when it gets there, go to another XY position. At the same time, monitoring the camera to see if any golf ball's in its path. If it is, we're going to tell the robot to go to the golf ball. So all this code, that doesn't have to be here, but it can be here more than likely. Okay? What we'll be doing, I mean, you can, if you're worried about how much code can sit inside this SWI highest priority, we're doing this exactly in exercise 3. We're going to set. So when we're inside here, we're going to set GPIO, I think it's 61, high here. Okay? Yeah, 1 second. And at the bottom of the function, I should say bottom of SWI, clear, or set GPIO 61 low. Yes?
What does it mean to post?
Yeah, good. I'm trying to get to that. That's what I want to try to get to. So yeah, let's explain that. But that's what we're going to do inside this function. And what needs to happen? Well, so that this software interrupt is functioning okay or correctly, it needs to every millisecond be able to run. If you put too much code in there, a post to software interrupt highest priority, another post up there is not going to cause a second software interrupt to run if the first one hasn't exited. Okay? So yes, we do have to be somewhat cautious, but again, the amount of code for your wall following, for your even searching through all those 228 LiDAR readings, that code will not take a huge amount of time. We're talking hundreds of microseconds, not not thousands of microseconds, the code you're going to write. If you start doing loops, say, over all the vision data, which we actually don't have on the red board anyway, but when we start, processing megapixel camera images, that's when you have to start worrying about your code taking a long time. Okay? Or, yeah, so anyway, really everything we're going to code on the red board is very fast code. So more than likely you don't have to worry about it. Okay, but yes, you're right. I'm going to come back to this in just a second, Kinga, but let's just think about what all happens in the software interrupt. Okay, so and we pull it high to time, but here we do our zeroing of the gyro readings, right? So we find for the first 2 seconds we do nothing. For the next 2 seconds we sum up all the readings that we get, and then finally after 4 seconds we find the 0 and always subtract that, don't we? So that we have a nice, at rest, 0 reading from the gyros. Okay, but then after that we'll do wall following. We'll do in lab 8 XY position control. Go to a XY position. Okay. We'll obstacle avoidance. So all this kind of stuff is going to be happening. So this state machine that we've started to do in homeworks, a big part of your state machine is going to be right in here. Okay? The robot's doing this state. Oh no, the robot now needs to go and do this state. This is where this is going to happen. Okay. Now, great. So all that stuff's happening now. So in other words, what we're going to do is by Lab 8, I know you guys, some of you have been saying, well, there's just so much code in our files. I get it. We're filling up a bunch of code, aren't we, in that main C file. So really, towards the end of the semester, this guy, along with maybe another software interrupt that brings in your LADAR data, this is where you're going to be putting most of your code. So maybe if you like just going all the way to the bottom of your C file, this is where this function should probably be at the bottom of your C file so you can find it easy. Because this is where you're going to be putting most of your code. Okay? Also, we are in Lab 8, I'm going to organize things a little bit more. Like all your optical encoder functions, your PWM functions, we're going to get those out of your main C file and put them in another C file. Okay? So anyway, we will organize things a little better so you're not just going nuts figuring out where to put things, especially for the final project. But anyway, okay. So this is where things get done. What's our issue? Okay, let's think about this. Why do we need to put it in a software interrupt? Okay, let's think about all the interrupts that are happening on this processor. Okay, so we just talked about two. We've got ADC, ISR. We've got the SPI, ISR. Now, these two are in order. So really, these don't affect our software interrupt. Because what we're going to find is this one happens, then this one happens, then our software interrupt happens. And more than likely, your software interrupt's done processing before this one's called again. Okay? So these two, in other words, these two probably can, but they're probably not interrupting your software interrupt. Okay? It's the other interrupts that we have to just, again, we have to take into account that they need to happen at a pretty good rate. So let's think about those. The most important ones, well, let's do the ones we're really familiar with. Timer 0's ISR. CPU timer 0. Timer 1's ISR. And timer 2's ISR. We may find a use for these, especially towards the end in the final project. Again, if there's a huge delay in when these occur, then they won't do what you're interested in. But more than likely, it depends, but you may set up one of these timers to happen at a pretty fast rate to sample the microphone or something like that. Okay? So it could be going pretty fast, and we don't want too much latency. In other words, what's the latency? If we tell the timer that we want to sample, if you're doing the microphone, maybe you're doing it at 10 kilohertz. And so every 0.1 milliseconds, you say, hey, I want to call timer 0. Right? We don't want too much latency in between there. Like if it takes, when we tell it to go, it's got to be in priority. Remember always, a hardware interrupt cannot interrupt another hardware interrupt. So if we're inside a hardware interrupt for a long time, then the time that timer 0 is called gets delayed. That's called latency. Because while that other hardware interrupt is running, yes, you can tell the timer interrupt to go, but it won't go until that other hardware interrupt has exited. Okay? All right. So anyway, we've got those three interrupts. And then the ones that are most important, or the ones that are faster, especially, is what? It's the UARTs. So our SCIA, this is our UART A. We got A, B, C, and D. Receive ISR. We have the SCIC receive ISR and the SCID ISR. Okay. By the end of the semester, right now, SCI-A is hooked up to that USB port that allows you to plug the red board into Teraterm, right? And print all that text to Teraterm from the robot. Well, we're going to change this by the end of the semester. By the end of the semester, your robot's going to be on the floor, and you won't be able to plug it into the USB anyway. Okay? And so what we're going to do is we're going to connect this to this. I'm going to soon be talking about the OpenMV camera. This is a camera that has processing capability right on board the camera. So we'll be getting, this is a Lab 8 thing, so we'll be getting into that. And the baud rate that we're going to use is 115/200. Okay? And SCI-C, yes, is our LiDAR. It is also communicating at 115/200. And finally, SCI-D communicates with the Raspberry Pi. 4. This is 115/200. Okay. So what this receive interrupt does, all these, it occurs when there is one character received from the device it's connected to. So how often is that happening? If we're sending data across, and remember, when we talk to the LiDAR, when the LiDAR is giving us data, I think it's something like 447 bytes that need to come across. And when it starts sending those, it just keeps on sending, one right after the other, until all 447 have been received by us, by the red board. Okay? So let's think about that. Remember, if we're sending over a byte on the UART, remember that is 10 bits, isn't it? Because of the start bit and the stop bit of what's called the RS-232 spec. All right, we talked about that before, and then 8 data bits. So, in other words, every character is how much time? That's 1 over 115/200 times 10, because it's 10 bits. Okay? This is each bit is 1 over 115/200 times 10. That equals what? So it's something like almost 100 microseconds. I think it's 86. Let's do it really quick. Calc. Yeah, so 1 divided by, well, I should just do 10 divided by 115/200. Yeah, so 86.8 microseconds. Okay, so I mean that's fast. That's not insanely fast, but it's definitely fast. So every 86.8 microseconds, which is 0.0868 milliseconds. Did that do that right? Yes, yes. Okay. So, I mean, most of the things we're doing is every millisecond, aren't we? Like our timer interrupts and all that kind of stuff. But this guy, especially when we're getting a lot of data, and just imagine when we're getting data from all 3 serial ports at the same time, which could be happening, right? We want to make sure that we're getting every data bit. Right? So we're not missing any interrupts and all this kind of stuff. Okay. So there we've got some speed. So if, for example, I don't know how many, a few of you have gotten to timing your software interrupt in exercise 3. Some people got that done. And when you look at the timings, you all will see this. It took about 20 microseconds to do the processing most of the time. But every once in a while, you'll see on the logic analyzer, it skips to about twice as long. So every once in a while, that software interrupt is taking, say, 40 or 50 microseconds to process. And just imagine if we allowed that software interrupt to do that code without being interruptible. If we did that one time that it took 50 microseconds for it to run, okay, these interrupts, it's highly likely that some of these interrupts would be skipped because they're running at every 86 microseconds. Okay? Or it'd be close. We'd be running in possible trouble somewhere. So then you go, oh, Dan wants me to implement the obstacle detection with the LiDAR. And you look at 64 LiDAR distances to try to decide if there's an obstacle in front of you. That just increased your code maybe another 15 microseconds. And then you start breaking more things, right? These interrupts. So the whole point of the software interrupt, if you get nothing else out of this lecture, is that this is a safe place to do longer code. Not insanely long code, but longer code. Code that takes, say, no more than, let's say, 400 microseconds to run. We'll throw that number out there. Okay, something like that. How would you know? The only way to know is by doing the timing with the logic analyzer. Okay. Anyway, okay. So, Kinga, what was your question again? Make sure I answer it.
What does it mean, the post?
The post, yeah, good. All right, yeah, very good. So, let's look at what I did with these software interrupts. So, if you go, let's see, we look at this table here. Where is it at? Peripheral map. Okay. If you recall, this is where the table we go to figure out what interrupt number is all our different things. Okay? And while I'm talking about this, I forgot to put up Code Composer. Let me pull up Code Composer real quick. Get that started. Okay. So technically, launch. Technically, what we're doing with these software interrupts are not real software interrupts. There are, have you guys heard of, what's the most popular one? But there's all sorts of real-time operating systems out there. The one that has been used a lot in the past, it's not coming to my mind. Wind River is the name of the company. It's been around for a long time. I can't think of their real-time operating system. But anyway, I'm going to show you, and I may not get to it today, I'm going long, but that's okay. Even in Linux and Windows and all this kind of stuff, there are what are called processes, threads, you may have heard them being called, things like that. There also, even in Windows and Linux, are interrupt routines. Okay? Usually those interrupt routines are down at the kernel level, and you don't touch them hardly ever, unless you're developing a new card that goes in the PC slot or something like that. Well, there are operating systems for embedded systems like this that allow for threading. Okay? So it's just some overhead code and all this kind of stuff. TI has an open source real-time operating. Real-time just means that when you say something happens at this time, it happens plus or minus some number of microseconds. It happens at that rate. That's what real-time, just think of it that way. So they have a real-time operating system called SWIs. And I'm always tempted, I used to teach the SWIs in this class, but I steered away from it this semester because when you run SWIs, you cannot. Remember how we have the option to put our code in RAM or in Flash? Well, when you run with this operating system called SWIs, it's so big that it only fits in Flash. So you can't set as many breakpoints. It takes a little longer to download your code to the robot and all this kind of stuff. So I chose not to go that route, and came up with my own little way of creating this thing called a software interrupt. SysBIOS has a thing called software interrupt, and that actually is completely in software, an interrupt that is completely in software. And the only way you can make that interrupt function happen is by posting it, Kinga. Okay? Now, so all that. But what I did is I went and looked at the interrupt map here. And I looked at these interrupts that I will probably never ever use. Some of these down at the end, the really lowest priority interrupts. And I just chose, I don't know, you could probably justify any of these, but I decided that I'm never going to use external memory with this red board. That's EMIF, external memory interface. And I'm assuming we're never going to get a correctable error from the RAM or from the flash. Maybe that's not a good assumption. Who knows? I've never played with that. So I have said, okay, I'm going to use this interrupt, this one and this one for 3 software interrupts. Okay? So just like we've set up, up above timer 0's interrupt, ADC A's interrupt, and all that kind of stuff, I set up these 3 interrupts so that I can post them, tell them to be called in software only. Remember, what did we say? Hardware interrupts. It was always something in hardware that caused that function to run. This thing I'm calling a software interrupt, you've got to force the interrupt in software. And so to do that, you're going to see when you get done with exercise 3, the way you do that is with this call. You say that the pi, what is it, pi, anyway, there's something like this, dot, IFR, no, that's what it is, sorry, I shouldn't have, that's right, I have my code composer up, let's do it there. So, let me show you, when you go here and acknowledge, let's go up here, so here's the interrupts that are enabled, right? There is another register, see if I can do this right here. Yeah, so pi control regs. So just by this, what this is saying, if you remember, this is saying, hey, enable this interrupt. Allow this interrupt to happen. Notice what I'm doing here. In the default code, I also interrupt 12.9. That was what this 12.9 is what we're calling the highest priority software interrupt. Okay? But anyway, how do you, in software, tell the interrupt to go? Is by doing the following. So say down in your timer or wherever, and actually I got a line here, right here, I commented out in the default code, this right here is how you would tell, control slash, this is how you would tell the software interrupt to occur. Now, yeah, I'm still getting there, King, I haven't described it yet. So what I did in exercise 3, I told you to create a function, maybe at the bottom or whatever, and I call it post SWI1. Okay, and all I put in there is this line. Okay, so what this says, yeah, see, and this is what, it's the pi, what's called interrupt flag register, not interrupt enable register, that's the IER. But the interrupt flag register, whenever that bit of the flag register is equal to 1, that means, hey, call that interrupt, but, and be careful here, call that interrupt whenever priority permits. If you think about that. Okay, so we have this. Okay, so now let's think about what happens. So if we have this function, and we go inside, say our timer or any interrupt routine, and I'm going to change this here to just call our function post SWI1 or whatever. I call it there. Now, look what happens. CPU timer 0 ISR is a regular interrupt routine, right? So when we get inside CPU timer ISR, no other interrupts can be called. All interrupts are disabled until we exit out of CPU timer 0 ISR. Yes?
The microprocessor that we are using, it has 2 CPUs, right? Is there any way that both of them can be linked so that whichever is the low priority software or whatever program that we are writing?
Yes, each CPU has its own interrupt vector table. And so they both can go on any interrupt. Both can fire on the same interrupt if you want to.
So can we run the software interrupt that which might take up more time?
On CPU 2?
Yes.
With a lot of work, yes. With a lot of work. And so we're not going to go there. But the biggest problem with CPU 2 is actually debugging your code more than anything else. And so, unfortunately, if you were going to work with both CPUs, we just don't have time in this class to do it, is what it is. If we're going to work with both CPUs, you would have to, when you debug every time in Code Composer, you have to download your code to CPU 1, and then you have to download your code to CPU 2. Then you have to start CPU 2's code, then you have to start CPU 1's code, and then you can debug. So it's a big process. And even if I just give you CPU 2 code, when you're using it in Code Composer, you still have to tell it to run. So it's just, it's not worth it right now since we don't need the processing time. But yes, absolutely, you could offload all sorts of code to CPU 2. If you were putting this in production or something like that, it's a great idea to do. Okay, it's just really hard to, it just becomes very tedious to debug. Yeah.
Also, there's this thing in TI processors which is CLA.
CLA, Control Language Accelerator. That is definitely another way we could add a software interrupt. Exactly. And that one's a little less hard to deal with. But you're right, it's another way to do this extra coding. Exactly. Yep, very good. But so that's another core. Remember we kind of talked about DMA being another core into this processor? This other thing called the Control Language Accelerator is another core that we could use. Again, probably not in the scope of this class. If you want to play with that, anybody for like their homework project or the final project, I have a CLA starter that you can look at. I also have CPU 2 starters in my examples, and you can see how you can use both CPU 1 and CPU 2 at the same time. So it's all there, just like you have lab starter, there's a CPU 2 starter and a CLA starter. But anyway, okay, so that's way past this class right now, okay? But good question. So back to this idea of posting. Okay. So we go in there and the timer 0 ISR every 50th time in there, we say, oh, yeah, it's equal to 0 mod 50. So we post software interrupt 1. All that did, Kinga and the rest of you, is it just simply set the flag register saying that when priority permits, you kind of see that? Because no interrupt can interrupt timer 0, when you say post SWI1, it does not mean to immediately jump to the SWI's ISR function. It can't. You see, it can't. It's not a call. It's not a function call. It is a post. It's saying do it when you can. And so what will happen is CPU timer 0's ISR will finish its code. It'll continue down, won't it? And it'll go all the way down to the bottom of it and exit. So it'll do all this stuff and then exit out of CPU timer 0. Now that it's exit out of CPU timer 0, that means interrupts are enabled again. It's possible your software interrupt function, its interrupt could be called at that moment. But what if there's another interrupt with higher priority? That higher priority interrupt's going to get called at that time and then run through its code, and when it exits, maybe then your software interrupt function could be called. Okay? Does that help a little bit with posting? You're just kind of saying, hey, hardware interrupt scheduler, you schedule this when you can, when you post it. Okay? All right, good. Now, but also the difference too is when you come into the software interrupt, and let's see if I have the, I think this is it. If you go, the ones that have these multiple, the 3 software interrupts, I'm doing a little fanciness that I found in a TI example. So, TI has this example. Where is it at? Software. Let me go find it. Control F, SWI1. Okay, keep on searching. Find. Here we go. This chunk of code that you will notice at the beginning of these software interrupts. What is this doing? Well, TI's got an example. So TI with this right here, they decided, oops, Control Z. They decided what priorities were the default priorities of the CPU right here, right? This is your lowest priority. 12 has the lowest priority. 1 has the highest priority. And then going 1.16's got the lowest priority of 1. 1.1 over here, the ADCA has the highest priority. That's what they just chose. Okay? Well, if you want to have some interrupts interrupt each other or interrupt another interrupt, that TI has supplied this example that allows that to happen. Okay? And what you have to do, it's, you know, a little bit involved here, but what's happening here? TI here is saving what interrupts are enabled, and then it re-enables interrupt 12. And then finally, the last most important thing is when you come into this highest priority software interrupt, it re-enables interrupts right here. Okay? So what that means, and by all this other these other assignments here, this is allowing certain interrupts to interrupt this function. Okay? So this is a function that's interruptible by any interrupt of higher priority. Well, the way I've set it up, I could set it up with any priorities. I could arrange this. It would be a little bit of a task, but I could arrange such that I change all the priorities of these interrupts here with their example. They even have a little script you can run, I think in Excel, that generates the code to give all the priorities the route you want. I can change it. All I've done is I've said that these three can be interrupted now by any of these other ones. That's the way I've set it up. Still, any of these other interrupts, they're not interruptible by anybody else. Once they're called, they finish before another interrupt can occur. But that's not the case for 1, 2, 3, these. I've set them up such that they have the lowest priority and they are interruptible. And then also the flow is the following. So how do we look at this? Software interrupt 1, which has the highest priority, is interruptible. By all what we're going to call hardware interrupts, all the other interrupts. So all interruptible by other hardware interrupts. Software interrupt 2 is interrupt by all HWIs and SWI 1. So SWI 1 could stop SWI 2 and finish its code. Do SWI 1 before SWI 2 is done. And then SWI 3 is interrupted by all HWIs and can be interrupted by software interrupt 2 and software interrupt 3. See that? And then we go, where the last place we can put information, put code, is in the mains while loop. Okay, and mains while loop interrupted by everything. So anything can interrupt the while loop. Interrupt by everything. Yeah. Did I screw it up? Yeah. Thank you. SWI 2 and SWI 1. Thank you. Okay. The main point here is that we have a place to put longer code that doesn't mess up the preciseness of and the latency of our more important interrupts that are collecting data, especially, right? We don't want to skip any of that data collection. Okay?